What is your address? Not your street name, not even your city. Where are you really? You are in a town, inside a country, on a continent, on a planet called Earth. Earth orbits a star, one of hundreds of billions, inside a system we call the solar system. Our sun is just one point of light in the swirling arms of the Milky Way galaxy, a grand spiral stretching over 100,000 light-years across. And yet, the Milky Way is merely one of many galaxies drifting together in a loose gravitational dance called the local group. It feels vast, but this is still just the beginning. Zoom out farther, and the local group is found nestled within the Virgo supercluster, itself just a branch of an even larger structure, the Laniakea supercluster. Hundreds of thousands of galaxies are drawn together into filaments that stretch across unimaginable distances. Together, these structures form what we call the cosmic web, a network of galaxies and voids, delicate yet immense. From your house to the outer edge of the known cosmos, everything is part of this intricate hierarchy. The question is not just where you are, but how you fit into this grand architecture of existence. Stand outside on a clear night and look up. The stars seem countless, but even the deepest view through the most powerful telescope reaches only so far. The observable universe, the part of the cosmos from which light has had time to reach us since the beginning, is a vast sphere surrounding Earth. Light travels fast, but the universe has been expanding ever since it began. So, while the light we see today began its journey over 13 billion years ago, the sources of that light have moved much farther away. As a result, the observable universe spans roughly 93 billion light-years in diameter. That is a staggering scale, nearly impossible to imagine. If Earth were the size of a grain of sand, the observable universe would be like a sphere the size of the entire planet. It contains hundreds of billions of galaxies, each with their own billions of stars and worlds. But this vastness is not chaotic. Instead, we find a curious kind of structure. At smaller scales, the universe appears clumpy. Galaxies gather in clusters, and those clusters stretch into filaments separated by enormous voids. But as we zoom out, something remarkable begins to happen. At scales of several hundred million light-years, the structure begins to smooth out, and beyond a certain point, about 1 billion light-years across, the universe appears homogeneous. That means, statistically, any given patch of space looks just like any other. The variations disappear. This phenomenon is known by a poetic name, the end of greatness. It marks the scale at which individual galaxies, clusters, and superclusters stop mattering. The cosmic tapestry becomes uniform, like a vast fog, dotted only gently with faint traces of structure. But why should the universe be uniform at such grand scales? That question lies at the heart of modern cosmology. The answer may lie in the very beginning of time, moments after the Big Bang, when the universe was smaller than a grain of dust. An event known as cosmic inflation may have stretched space so rapidly that tiny quantum fluctuations were smeared across unimaginable distances. These fluctuations became the seeds of galaxies and superclusters. But the rest, the enormous canvas around those seeds, was left astonishingly smooth. This uniformity gives cosmologists a powerful advantage. It means that when we look in any direction, we are seeing a representative sample of the cosmos. Our region is not special. It is not unique. This idea, called the cosmological principle, is foundational to our understanding of the universe. It allows scientists to model its evolution, map its geometry, and even estimate its age. But it also leads to a deeper, more philosophical truth. The further out we look, the more we realize how ordinary we are. And yet, within this uniformity, subtle patterns remain. Ripples in the distribution of galaxies, slight temperature fluctuations in the cosmic microwave background. These are the echoes of ancient processes: gravitational tugging, baryon acoustic waves, quantum jitter, that shaped the structure we see today. They remind us that even in a universe that becomes uniform at the largest scales, complexity still emerges from simplicity. Order arises from near-perfect chaos, and within that balance, we find the roots of everything. In the early 16th century, a quiet revolution began in the mind of a man named Nicholas Copernicus. While studying medicine in Italy, he spent his evenings reading Aristotle and pondering the structure of the cosmos. What he imagined was heretical at the time, that the Earth was not the unmoving center of creation. Instead, he proposed that Earth was just one planet among others, all orbiting the Sun. He knew this idea would challenge centuries of belief, and so he hesitated to publish it. But when he finally did, the world would never see itself the same way again. The Copernican revolution did more than just rearrange planets. It redefined our place in the universe. Earth was no longer the cosmic throne of humankind, but a moving speck in a vast, indifferent sky. At first, this seemed to diminish us. How small we must be if our world is just one of many. But over time, the idea became liberating. If Earth is not unique, then perhaps life, complexity, and intelligence might also exist elsewhere. The Copernican Principle, as it became known, holds that we do not occupy a privileged position in the cosmos. Today, the Copernican Principle is a cornerstone of modern cosmology. It tells us that the laws of physics should be the same everywhere, that the view from a distant galaxy would reveal much the same universe as the one we see from here. This assumption is not just philosophical, it is testable. And in the past century, it has been repeatedly confirmed by observations. From the distribution of galaxies to the patterns in background radiation, the universe appears remarkably uniform when viewed at large scales. Perhaps the strongest confirmation of the Copernican Principle comes from the cosmic microwave background radiation, a faint afterglow left over from the early universe. No matter where we look in the sky, this radiation has almost the same temperature, about 2.7 degrees Kelvin. The variations are tiny, only 1 part in 100,000. That kind of uniformity suggests that the universe has no preferred direction, no favored center. Our cosmic location is not special. We are adrift in a sea of sameness. This realization reshapes our perspective. We once imagined the universe as built around us, a divine architecture with Earth at its heart. Now we understand that the universe operates under general rules, rules that do not care where you are or who is observing them. That kind of humility is not a weakness of science. It is one of its greatest strengths. By accepting that we are ordinary, we gain the power to make extraordinary predictions. And those predictions about the age, shape, and fate of the cosmos have proven remarkably accurate. Still, the Copernican Principle is not merely a scientific tool. It is a way of thinking, a lens through which we see the universe not as something designed for us, but as something we are part of. It teaches us to look outward with curiosity and inward with restraint, to be skeptical of our assumptions, and to measure our place not by size, but by insight. From the writings of Copernicus to the satellite data of modern telescopes, this principle has guided our journey from the center of the universe to the edges of the known and beyond. The universe, at its largest scale, appears like a grand web, a tapestry of galaxies stretching across space in delicate, interconnected filaments. But this vast architecture did not always exist. At the very beginning, the cosmos was hot, dense, and incredibly smooth. Any differences in temperature or density were almost imperceptible. And yet, these tiny variations, quantum ripples in an otherwise uniform sea, became the seeds of everything. Galaxies, clusters, and superclusters all trace their origins to these minuscule fluctuations. How can such small irregularities give rise to such magnificent structures? The answer lies in the relentless force of gravity. Even the slightest concentration of matter pulls more matter toward it. Over time, dense regions become denser, attracting gas, dust, and eventually stars. These stars gather into galaxies, and galaxies themselves are drawn together into clusters. Clusters stretch into elongated filaments, woven together by gravity, separated by vast empty regions we call cosmic voids. Together, they form what we now call the cosmic web. But gravity was not acting alone. While it worked to clump matter together, the expansion of space was pulling everything apart. This cosmic tug-of-war between attraction and expansion has shaped the universe's structure for billions of years. In the earliest moments, expansion was violent and rapid. Then it slowed, allowing gravity time to gather material into galaxies. In recent epochs, expansion has accelerated once more, driven by a mysterious force known as dark energy. Still, the scaffolding laid down by gravity remains. Astronomers have mapped this vast structure in exquisite detail. Using telescopes and spectrographs, they have traced the positions and motions of hundreds of thousands of galaxies. These maps reveal a universe that is not random. Galaxies are not scattered like dust in the wind. They follow a pattern. Filaments stretch across hundreds of millions of light years. Superclusters appear as hubs within the network. Between them are yawning voids, where few galaxies dwell. The cosmic web is the skeleton upon which all large-scale matter is arranged. One of the most extraordinary features of this structure is how scale-dependent it is. At smaller scales, planets, stars, individual galaxies, the universe appears chaotic. Objects move, collide, orbit, and explode in unpredictable ways. But as you zoom out, order emerges. Patterns begin to form. Relationships become visible. The universe transitions from noise to structure, from randomness to design. And this emergence is not imposed from outside. It arises naturally, governed by fundamental physical laws, acting over unimaginable spans of time. The story of the universe is, in many ways, the story of contrast, of light and dark, matter and void, simplicity and complexity. From quantum fluctuations smaller than an atom came structures stretching over billions of light years. From the chaos of early plasma, shaped by expansion and sculpted by gravity, emerged spirals, clusters, and walls of galaxies. No one planned this pattern. It arose spontaneously, as though the universe itself were solving an equation we have only just begun to understand. And so, from the smallest imaginable scales to the largest structures we can observe, there is continuity. The ripples of the early universe have echoed outward across time, becoming the architecture of everything we see. When we map the heavens, we are not just drawing star charts, we are reading the record of how order emerged from chaos. The cosmic web is not merely a structure, it is a story. One written in gravity, drawn in light, and still unfolding in the vast silence of the night sky. When we look at the night sky, no matter which direction we choose, we encounter the same faint glow, the cosmic microwave background radiation. This relic light, emitted when the universe was just a few 100,000 years old, has nearly the same temperature in every direction. That temperature is around 2.7 degrees Kelvin, with variations so small they are barely detectable. It is as if the entire sky agreed on a single thermostat setting. But how could regions of space so far apart possibly have come to the same temperature? This is the horizon problem. It arises from a simple question. How could distant parts of the universe, which have never been in contact, know to be so similar? If two regions are now separated by tens of billions of light years, and if the universe is only 13.8 billion years old, there has not been enough time for light, or anything else, to travel between them. No signal, no interaction, no exchange of energy. And yet, they match. They are in thermal equilibrium, like two cups of tea poured from the same kettle. In classical physics, for two objects to reach the same temperature, they must interact. They must exchange heat until balance is achieved. But in the early universe, the distances were already too vast for this to occur, unless there was some unknown mechanism that connected all regions before they became separated. This puzzling mismatch between theory and observation demanded an explanation, one that could stretch causality across the cosmos and make the uniformity of the sky no longer a coincidence, but a consequence. The most powerful idea to emerge from this dilemma is known as cosmic inflation. Proposed in the early 1980s by physicist Alan Guth, inflation suggests that, in the tiniest fraction of a second after the Big Bang, the universe underwent an unimaginably rapid expansion. Space itself did not simply grow, it exploded. In far less than the blink of an eye, the observable universe ballooned from subatomic size to something larger than a galaxy. Distances between points expanded faster than the speed of light, not a violation of relativity, but a consequence of how space itself behaves. This expansion did not move matter faster than light. It stretched the very fabric of the universe. In doing so, it took regions that had once been in close thermal contact and flung them far apart. This means that those now distant areas of the sky were once close enough to exchange energy, to synchronize temperatures, and to settle into equilibrium. Inflation elegantly explains how the cosmos could appear so uniform, even though its farthest parts are forever out of reach of one another. Inflation also solves another mystery: the flatness of the universe. Observations show that space is not curved in any detectable way. On the largest scales, the geometry of the cosmos is flat, like an infinite sheet, not spherical, like a globe, or curved like a saddle. Without inflation, such perfect flatness would be an improbable coincidence. But inflation, by stretching space so quickly and so violently, would have ironed out any curvature. Just as a balloon, when inflated, appears flatter and flatter as it grows. Despite its beauty, inflation is a bold and extraordinary claim. It requires a new kind of energy, a field with unusual properties, called the inflaton. This field, theoretical though it may be, would have caused space to expand exponentially and then decay, transferring its energy into the particles that now fill the universe. We have not detected the inflaton directly, but its fingerprints may be present in the faint patterns of the cosmic microwave background. The small fluctuations, those tiny hot and cold spots, may be echoes of quantum ripples stretched across the cosmos. Inflation gives us a universe that is smooth, flat, and filled with structure. It bridges the gap between quantum uncertainty and galactic grandeur. It connects the unimaginably small with the incomprehensibly large. And yet, for all its explanatory power, the evidence remains circumstantial. We continue to search for stronger proof, for gravitational waves from the early universe, for traces of primordial quantum noise. But if inflation is correct, then every star, every galaxy, and every breath we take owes its existence to a moment of incomprehensible expansion, a whisper at the dawn of time that became the cosmic roar of everything. The quest to understand the structure of the universe began with a question as old as civilization itself. What is out there, beyond what we can see with our eyes? For thousands of years, we relied on our senses, then on telescopes of glass and steel. But to truly map the cosmos, to see the birthmarks of the universe itself, we needed to rise above Earth's atmosphere. In the late 20th century, humanity launched a new kind of eye into space. Not a lens, but a sensor. Not a telescope, but a time machine. In the year 1989, the Cosmic Background Explorer, or COBE, was launched into orbit. Its mission was profound and deceptively simple: to measure the faint afterglow of the Big Bang with greater precision than ever before. What it found stunned the scientific world. COBE detected tiny temperature fluctuations in the cosmic microwave background, ripples in the sky that were just 1 part in 100,000. These were the earliest structures in the universe, frozen in light. It was, in a very real sense, the first baby picture of the cosmos. The results from COBE were so significant that 2 of its lead scientists, John Mather and George Smoot, were later awarded the Nobel Prize in Physics. But the picture, though revolutionary, was still blurry. To sharpen it, another satellite was sent into orbit in the early 21st century. The Wilkinson Microwave Anisotropy Probe, known as WMAP, revealed the same fluctuations in much finer detail. What once looked like a fog now appeared as a pattern. There were hints of structure, peaks and valleys, like a cosmic fingerprint imprinted on the sky. Then came Planck, launched by the European Space Agency in the year 2009. Planck had one purpose: to give us the most precise map yet of the early universe. With it, scientists could measure the age, composition, and curvature of the cosmos with astonishing accuracy. It confirmed that the universe was born in a hot, dense state, and that it has been expanding and cooling ever since. But more than that, it revealed that the universe was not only filled with matter, it was filled with information, encoded in light. While space telescopes like COBE, WMAP, and Planck scanned the sky for ancient radiation, other instruments mapped the present-day universe in 3 dimensions. One of the most ambitious of these projects is the Sloan Digital Sky Survey. Perched on a mountaintop in New Mexico, it did something extraordinary. It turned light into maps. Astronomers began by capturing optical images of thousands of galaxies. But to truly understand their distances and motions, they needed to analyze their spectra, the unique rainbows of light each galaxy emits. To do this, they used a clever method. For every section of sky, they created an aluminum plate, custom drilled with tiny holes, each aligned with a galaxy. Fiber optic cables were placed through each hole, directing the light to sensitive spectrographs. These devices could read the spectrum of each galaxy, determining not just its composition, but how fast it was moving and how far it had traveled. It was as if the universe had spoken in color, and we had finally learned how to listen. Over time, more than 10,000 plates were drilled, each one capturing a unique slice of the cosmos. Together, they revealed a universe of astonishing scale and detail, a web of galaxies stretching across the heavens, with dense clusters, vast voids, and filaments spanning hundreds of millions of light years. It was the first time we could see the structure of the universe, not just as theory, but as cartography. The celestial sphere was no longer a mystery. It was a map, and we had begun to chart its terrain. These telescopes, space-based and earthbound, transformed our view of the universe. From blurry smudges of ancient heat to crystalline patterns of galactic structure, they showed us that the cosmos is not only vast, but coherent. It has a memory, and it leaves traces. Each photon carries a story, each galaxy marks a chapter, and each survey brings us closer to understanding the epic narrative we inhabit. In mapping the universe, we are not merely observers, we are explorers, charting a continent made not of land, but of light, space, and time. As astronomers began mapping the universe in ever-increasing detail, a strange question emerged from the data. What exactly is the universe shaped like at the largest scales? Not the shape of space itself, but the structure of the matter within it. Galaxies do not float randomly. They form clusters, filaments, and vast walls. But what is the best metaphor to describe this distribution? Surprisingly, some of the brightest minds in cosmology turned to the kitchen for inspiration. Thus began a spirited debate. Is the universe made of meatballs, pancakes, or sponge? The American school of thought, led by physicist Jim Peebles, proposed what became known as the meatball model. In this view, matter clumps into roughly spherical concentrations, like meatballs, scattered in an otherwise low-density soup of space. Galaxies and clusters are the meatballs. The voids between them are the broth. This was a bottom-up model. Small structures form first, and over time they draw in more matter, eventually giving rise to the vast cosmic architecture we observe today. Meanwhile, behind the Iron Curtain, a very different theory was forming. Yakov Zeldovich, a brilliant Russian physicist who had once worked on the Soviet atomic program, envisioned a universe of two-dimensional structures. He imagined matter collapsing into vast, thin sheets, cosmic pancakes, spread across space. Where these pancakes overlapped, galaxies would form. In Zeldovich's model, the large-scale structure comes first. Galaxies are not the cause of the pattern, they are the consequence. A universe built on walls, not balls. These two ideas were more than metaphors. They reflected fundamentally different philosophies about how structure forms. Peebles believed in gradual clumping, driven by small fluctuations and the steady pull of gravity. Zeldovich believed in large-scale collapse, where gravity amplified two-dimensional instabilities to form walls of matter. Each side had its advocates, and their debates stretched across conferences, continents, and decades. Yet neither model seemed to capture the full complexity of what the telescopes were beginning to reveal. Then, in the 1970s, an unlikely mediator entered the scene. Martin Rees, an English cosmologist, moved freely between American and Soviet academic circles. One of his postdoctoral researchers, a soft-spoken man from Kentucky named Richard Gott, took the competing ideas and proposed a new one. Gott suggested that the structure of the universe is not dominated by spheres or sheets, but by something in between, a sponge. In this model, high-density and low-density regions are complementary and connected. It is not meatballs or pancakes, it is both and neither. Imagine a three-dimensional sponge. It is filled with tunnels, walls, and hollow chambers. Some regions are thick with material, others are nearly empty. The sponge model suggested that matter and voids form a complementary network, with galaxies tracing the borders of empty spaces. As the Sloan Digital Sky Survey and other mapping projects advanced, the sponge began to look more and more like reality. Filaments of galaxies surrounded vast voids, forming an interlocking web. This was not theoretical any longer, it was visible. What is remarkable about this evolution in thinking is not just the shift in metaphor, but what it reveals about science itself. Competing models can exist for years, each partially right and partially wrong, until data brings clarity. The universe, as it turns out, does not care about our analogies. It simply follows its own logic: gravity, expansion, and the imprint of quantum fluctuations. But our human minds, shaped by stories and images, still need metaphors. And sometimes, metaphors from the kitchen prove surprisingly powerful. Today, cosmologists use advanced simulations to recreate the growth of cosmic structure. These simulations show sponge-like patterns forming naturally under the influence of gravity and dark matter. What began as playful imagery, meatballs, pancakes, sponge, has matured into mathematical precision. Yet the simplicity of those words still holds power. They remind us that even the grandest structures in the universe can be approached with curiosity, creativity, and just a hint of humor. In the end, the cosmic web is not only a scientific achievement, it is a human one. Before galaxies, before stars, before even atoms as we know them, the early universe was a dense, glowing sea of particles. In this seething plasma, photons and baryons, particles like protons and neutrons, were tightly coupled, constantly colliding in a high-energy dance. Gravity pulled matter inward, while radiation pushed outward, creating a delicate balance that gave rise to pressure waves rippling through the hot primordial soup. These were sound waves, but not like any we could hear. Colossal baryon acoustic oscillations moving through the infant universe. Imagine a pebble dropped into a cosmic ocean. From every dense region of matter, waves expanded outward in all directions, like ripples across the surface of a still pond. These waves carried energy, shaping the structure of the early cosmos. But the medium was not water. It was a plasma so hot that light itself could not move freely. Photons scattered off electrons constantly, keeping the universe opaque. Only when the cosmos cooled enough for atoms to form, several 100,000 years after the Big Bang, did the waves freeze in place, leaving behind a fossil-like imprint. At that moment of decoupling, when electrons settled into stable orbits around nuclei and photons were finally released to travel freely through space, the universe became transparent. The ripples in the plasma stopped moving. The matter that had been pushed outward by radiation formed shells, thin, spherical structures centered around the original overdense regions. Most of the ordinary matter collapsed back toward the center, drawn by gravity. But a small fraction remained at the edges of these ripples, caught in a frozen snapshot of the universe's earliest acoustics. Over billions of years, these subtle differences grew. Gravity amplified the initial variations, drawing matter into galaxies and clusters. And those early ripples? They left a signature, a preferred separation between galaxies, a faint but measurable pattern. When astronomers today measure the distances between large numbers of galaxies, they find that one particular scale appears more often than others. That scale is about 150 megaparsecs, a vast distance, but one that matches perfectly with the radius of those primordial sound waves. This regular spacing, this cosmic rhythm, is what we now call baryon acoustic oscillations. It is an ancient echo, not in sound, but in structure. The peaks and valleys of those long extinct waves still guide the arrangement of galaxies across the universe. And because the physics behind them is so well understood, baryon acoustic oscillations have become one of cosmology's most precise tools. By measuring their imprint, scientists can trace the expansion of the universe, understand dark energy, and even check the accuracy of models describing cosmic evolution. In a universe shaped by invisible forces and unimaginable distances, it is astonishing that we can still detect the pulse of its earliest moments. These waves, born in a plasma too hot for light to escape, now shape the heavens in patterns we can map. In their frozen rhythm lies a record of creation, one that connects the deepest past to the present structure of space. And so, every time we measure the gap between galaxies, we are not just observing the cosmos, we are listening to its first breath. There is a silent presence that moves through the universe. It does not shine, it does not glow, and it does not reflect light. Yet it is everywhere. It surrounds galaxies, shapes their motion, sculpts the cosmic web, and holds the universe together. This presence is called dark matter. Though it cannot be seen directly, its influence is overwhelming. It is the scaffolding on which galaxies form, the glue that holds clusters intact, and the silent architect of structure itself. Without dark matter, the universe as we know it would not exist. The first clues came in the early 20th century, when a Swiss astronomer named Fritz Zwicky studied a distant cluster of galaxies known as the Coma Cluster. Zwicky calculated its total mass in two ways. First, by counting the visible light from the galaxies, and second, by measuring how fast those galaxies were moving. The results did not match. The galaxies were moving far too fast to be held together by the gravity of the visible matter alone. Zwicky concluded that some unseen mass, what he called dunkle materie, must be present. At the time, few took Zwicky seriously. His ideas were bold, and his personality was difficult. But decades later, another astronomer would make a discovery that echoed his conclusions. Vera Rubin, working in the 1970s, was studying the rotation curves of spiral galaxies. According to Newtonian physics, stars farther from the galactic center should orbit more slowly, just as planets in the outer solar system move more slowly than those near the sun. But Rubin saw something strange. The stars on the outskirts of galaxies were moving just as fast as those near the core. This was not supposed to happen. The gravitational pull from the visible matter alone was not enough to explain such speeds. The stars should have been flung out into space, but they were not. Something unseen was providing the extra gravity, something massive yet invisible. Rubin's observations confirmed what Zwicky had long suspected. The universe was filled with matter that did not emit light. Over time, these findings reshaped our understanding of the cosmos. Today, we believe that dark matter makes up about 85% of all matter in the universe. But what is dark matter? That remains one of the greatest mysteries in science. It is not made of the same kind of particles that form atoms. It does not interact with light or the electromagnetic force. It passes through ordinary matter without leaving a trace. The leading hypothesis is that dark matter is made of particles called WIMPs, weakly interacting massive particles. These particles would be like neutrons or protons in mass, but invisible to all forces except gravity. They would float silently through space, pulling on stars, galaxies, and clusters. To find these particles, scientists have built detectors deep underground, shielded from cosmic rays and background noise. They have sent satellites into orbit, built particle accelerators to recreate early universe conditions, and created tanks filled with noble gases to catch the rare interaction of a WIMP with regular matter. And yet, so far, the particles have not revealed themselves. The universe continues to whisper their presence through gravity, but the particles remain silent. We can feel their pull, but we cannot yet touch their nature. Despite the lack of direct detection, the evidence for dark matter is overwhelming. It is not only needed to explain galaxy rotation, it also explains the behavior of galaxy clusters, the bending of light in gravitational lensing, and the distribution of temperature fluctuations in the cosmic microwave background. In simulations of cosmic structure formation, without dark matter, the galaxies do not form. With it, they form naturally, beautifully, and in ways that match what we see in the sky. Dark matter makes the universe coherent. We also know that dark matter forms vast halos around galaxies, giant spheres of invisible mass extending far beyond the visible edge. Our own Milky Way galaxy is believed to be wrapped in a dark matter halo that stretches hundreds of thousands of light years across. These halos are not only large, they are essential. Without them, galaxies would be unstable, torn apart by their own rotation. With them, galaxies become stable, long-lasting islands of stars in an ocean of gravitational balance. In many ways, dark matter is the protagonist of the cosmic story. It is the quiet force behind the formation of structure, the hidden thread connecting galaxies, and the invisible hand that sculpts the universe. It is a mystery, yes, but not an absence. It is a presence we have yet to see, but one that we cannot ignore. The more we learn about it, the more we realize the universe we know, the stars, the planets, and ourselves, are only the visible surface of a much deeper, darker foundation. And the search to understand it is only just beginning. We tend to think of ourselves as still. The Earth turns slowly beneath us. It orbits the Sun in a gentle ellipse. The Sun, in turn, revolves around the center of the Milky Way. But this is only the beginning. Our galaxy, along with its neighbors, is not fixed in place. It is hurtling through space. And when astronomers measured our movement relative to the cosmic microwave background, the light left over from the birth of the universe, they discovered something remarkable. We are not just drifting, we are racing. The numbers were staggering. Our local group of galaxies is moving at over 1,000 kilometers per second, rushing toward a region of space in the southern sky. This region, hidden behind the dust of the Milky Way, was once invisible to our telescopes. But through careful observations in the X-ray spectrum, astronomers identified a massive concentration of galaxies. They called it the Great Attractor. Its gravitational pull is so strong that it bends the motion of entire clusters, drawing them across hundreds of millions of light years. But the mystery did not end there. As astronomers expanded their surveys, they realized that the Great Attractor itself is not stationary. It too is being drawn by something even more immense, the Shapley Supercluster. This Leviathan structure, located roughly 600 million light-years away, contains the mass of more than 10,000 Milky Way galaxies. Its gravitational field dominates the surrounding region, influencing the flow of matter across intergalactic space. In a sense, it is the true heavyweight behind the motion we observe. The pattern is breathtaking. Our galaxy, our local group, and our supercluster are all flowing together in a grand cosmic river. This motion, observed across hundreds of millions of light-years, has been called the dark flow. And yet, gravity alone may not tell the whole story. In the opposite direction from the Shapley Supercluster lies a vast, empty region of space. It contains almost nothing, no clusters, no filaments, just an immense void. This underdense region, known as the dipole repeller, may be playing an equally important role. The dipole repeller does not push in the way gravity pulls, but its emptiness creates an imbalance. With less mass to hold galaxies in place, the surrounding structures accelerate away from it. This means that we are caught between two cosmic forces, one pulling, the other releasing. Between the Shapley Supercluster and the dipole repeller lies a gravitational tension stretching across nearly 1 billion light-years. It is a current, a flow of galaxies, drawn toward density and away from void. This discovery has reshaped our understanding of motion on the largest scales. The universe is not a static stage, but a dynamic, moving fabric. Galaxies drift not only under local conditions, but as part of massive flows shaped by the overall distribution of matter and emptiness. We are not merely orbiting our star. We are part of a river of galaxies, cascading through space, drawn by structures we can barely see. And like leaves on a cosmic tide, we are carried forward, destination unknown. In science, patterns are welcome. Anomalies, however, are unsettling. The cosmic microwave background, the ancient light left over from the birth of the universe, has given us a picture of near-perfect uniformity. Its faint fluctuations have been mapped with exquisite detail by satellites such as WMAP and Planck. These fluctuations are understood to be the seeds of all cosmic structure, and they match our expectations beautifully, except for one detail. A strange alignment, a cosmic coincidence, a mystery that some scientists have come to call the axis of evil. The name, although dramatic, refers to a very real and persistent problem. When astronomers divide the microwave background into large-scale patterns, called multipoles, they notice something strange. The quadrupole and octupole moments, which should be randomly oriented, seem to point in the same direction. Even stranger, that direction happens to be eerily close to the plane of our own solar system, the ecliptic. The cosmic sky, it seems, is aligned with our backyard, and that is not supposed to happen. According to the Copernican Principle, no place in the universe is special, not Earth, not the Sun, and certainly not the plane in which our planets orbit. The laws of physics should look the same in every direction. Yet this unexpected alignment appears to break that rule. If the oldest light in the universe is somehow biased toward our solar system's orientation, then either the observations are flawed, or our most fundamental assumptions must be questioned. Neither option is comforting. At first, scientists hoped the anomaly was a mistake, a result of noise, dust, or some artifact in the data. After all, the galactic foreground, filled with radiation and magnetic fields, could interfere with our measurements. Perhaps the instruments were not sensitive enough, or the analysis techniques introduced bias. But year after year, as new satellites confirmed the findings, the anomaly persisted. Even with better instruments, cleaner data, and more sophisticated models, the alignment refused to vanish. Some suggested that the coincidence was merely psychological. Humans are natural pattern seekers. We see faces in clouds, animals in constellations. Perhaps this alignment was simply another illusion. But the statistical significance of the result has been carefully examined, and while not universally agreed upon, many experts now believe the anomaly is real. It is not necessarily a flaw in the instruments, nor an error in the theory. It is, instead, something that exists, and we do not yet understand why. If the axis of evil is real, it may have deep implications. It could mean that the universe is not as isotropic as we assumed. Perhaps there is a subtle, large-scale structure imprinted on space itself. Or perhaps something in the early universe created a preferred direction, some unknown field, or an interaction we have not yet discovered. There are even speculative theories involving topology, quantum entanglement, or multiverse collisions. For now, these remain in the realm of ideas, not evidence. Science thrives on questions, and the axis of evil is one of the most intriguing in modern cosmology. It may one day be explained away by better measurements or a deeper understanding of foreground interference. Or it may lead us to a profound shift in how we view the cosmos. Until then, it remains a quiet rebellion in the sky, a faint whisper from the edge of time, suggesting that the universe may still hold secrets not yet written in our equations. Sometimes, it is the smallest deviation that points to the greatest discovery. Cosmic inflation explains much: the smoothness of the universe, its flat geometry, the origin of structure itself. But what caused inflation? What triggered this brief, furious expansion that transformed the universe from a subatomic point into something vast beyond imagination? One idea points to a strange substance known as vacuum energy. Unlike ordinary energy, vacuum energy does not vanish when space is emptied. Instead, it persists, filling the void with latent potential. In certain conditions, this energy may become unstable, igniting a sudden release, a spark that creates a universe. This spark, once ignited, inflates a bubble of space at exponential speed. Inside this bubble, temperatures fall, particles emerge, and the seeds of stars and galaxies are planted. Our universe may be one such bubble, born from a quantum fluctuation in a sea of vacuum energy. But if it happened once, why not again? Inflation may not be a singular event. It may be eternal. In this view, space is constantly inflating in some regions, while in others, bubbles like ours form and grow, each one expanding into its own distinct universe. This is the idea of the multiverse. If true, the multiverse changes everything. It means our universe is just one of countless others, each with different properties, different laws, perhaps even different dimensions. Some may be empty, others chaotic, others lifeless. Some may contain stars without planets, or time without matter. In rare cases, perhaps conditions are just right for galaxies to form, stars to burn, and life to ask questions. In this vast landscape, we occupy a bubble where consciousness is possible, not because it is special, but because only such bubbles can be observed from within. But can we test this? Can we see beyond the boundary of our cosmic bubble? The answer, for now, is unclear. Some have proposed that if two universes collided in the early moments of inflation, the impact could leave a scar, a faint circle or cold spot, etched into the cosmic microwave background. So far, no such evidence has been found, and yet, the possibility remains. We may never hear the voices of other universes, but their presence might still echo in the sky. In seeking the cause of inflation, we may have opened a door to infinity. We have come a long way in understanding the cosmos. Gravity, dark matter, dark energy, and inflation. Each principle has revealed a part of the grand puzzle. We have mapped the web of galaxies, measured the age of the universe, and captured the faint glow of its birth. Through mathematics and observation, we have traced the forces that shape everything from atoms to superclusters. And yet, every answer leads to a deeper question. The more we uncover, the more the unknown expands around us, like the night sky itself. This journey is guided by minds both past and present. Copernicus showed us we are not the center. Vera Rubin taught us to trust what cannot be seen. Jim Peebles revealed the subtle architecture behind chaos. Each discovery stands on the shoulders of countless others, scientists who dared to ask, dared to doubt, and dared to look beyond what is comfortable. Their work has built a framework we now rely on, a cosmic narrative written not in myth, but in measurement, precision, and light. And yet, we still stand at the edge of mystery. We do not fully understand dark energy. We have not found the true nature of dark matter. Inflation remains a theory without a definitive trace. The multiverse lies just beyond our grasp. But these gaps are not failures, they are invitations. The universe still whispers through gravitational waves, flickering quasars, and the silence of empty space. It is not finished speaking. We are not finished listening. The story continues, written in starlight, waiting to be read. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.